Hey guys, Jake here, coming at you with another math problem today. Today I'm going to be showing you how to find the work required to pump the water out of the spout if you're given some sort of a tank. Like in this case, we have this spherical tank that we can see has a radius of 3 meters, and then there's the spout sticking out the top of it, which is 1 meter long. But these kind of work problems come up a lot in Calc 2, and figuring out how to find the work required to pump water out of a spout, or just to pump water out of a tank in general. So I want to show you an example of that. And this is actually also one of the formulas mentioned on my Calculus 2 study guide. There's a link down in the description if you want to check that out, but you can go download that right away. It's available for instant download. It'll be a PDF that you can print or save. It's only a couple bucks, so it's very affordable, but this is one of the formulas on there, or this uses one of the formulas on there. So the formula on my study guide that's mentioned on there is that work is force times distance. And the kind of weird thing about these kind of problems is that formula itself doesn't really give you a whole lot of information, so that's why I wanted to show you an example of how to actually apply that. So really, when it comes to figuring out the work required to pump water out of a tank, really what that comes down to is setting up an integral which represents the work required to do this. But when you're setting that integral up, you have to kind of go about it step by step and kind of work your way through the different steps. So we're not going to go straight to the formula for work quite yet. So what we actually want to do first is kind of imagine as water is being pumped out of this tank. Basically what's going to be happening is you can imagine a bunch of little discs, basically, as you work your way up this, work the water out of this spout. You can kind of imagine all these little discs as you go down. And each little disc is basically an infinitely thin cylinder, which represents all the water basically that sits in that layer of our tank. So you can kind of imagine, instead of thinking of this as a sphere, think of it as a bunch of really, really thin cylinders stacked on top of each other that make the shape of a sphere. And the reason why we want to think of it like this is each disc, each layer of water in this tank is going to require a certain amount of work based on the fact that all the water in that layer has to be pumped up the same distance, right? All the water on this layer is going to be the same distance from the top of the spout where we're trying to get that water to. So basically, what we're going to be doing is figuring out an equation which represents the amount of work required to pump a specific disk out of this tank. And then what we're going to do is sum up all those works that it takes to get each disk, and that would be the work that it takes to get all the disks of water out of the tank. So to do this, what we want to do is come up with a new variable, basically, which represents the distance that any given layer of water has to be pumped out. So basically that distance is going to be the distance from whatever layer of water we're looking at up to the top of the spout. So basically this distance here. And you can imagine, these different discs as we go throughout this whole thing are all going to have a different distance, right? The disc down here is going to have to be pumped further than the disc up here. But basically this distance, we'll just call it xi star, is typically how you see that named. But this xi star is just going to represent the distance that the xith layer, so we'll say this is the xith layer, has to be pumped. So once we have this variable that represents the distance that the ith layer has to be pumped up, what you want to do is figure out an equation for the volume of that layer. So basically we want to come up with a volume for the ith layer of the liquid, and this is going to be based on xi star, because you can see as you go throughout this sphere here, the radius, or the radius of the individual disk, so the distance from the center of the disk to the edge of the disk, is much shorter at the top and the bottom of the sphere, and much longer in the middle of the sphere, right? In the middle we know it's 3 meters, but up here it's going to be shorter, and down here it's going to be shorter. So the volume of each disk is going to be different depending on how far down into the tank you are, right? Because the volume of each individual disk is basically just going to come from the volume of a cylinder equation, which is pi r squared times the height. So this radius is going to depend on how far down into the tank we are. So what we need to do is come up with an equation which depends on xi star, which represents the radius of that specific disk. So to do that, what we can do actually is imagine graphing this circular shape and spout basically on an xy axis. So we'll just kind of do that over here real quick. And actually what I'm going to do is kind of tilt it sideways. So imagine this circle over here where we have it like this, right? Where we have our spout coming out here, going to the origin, and then we have our sphere over here, which is centered on the x-axis, and then we have the y-axis over here. So we know that this has a radius of 3 meters, and basically we know that it's 1 meter away from the y-axis here. So I haven't scaled this very well, but we know that this is going to be x equals 1 because we know that the spout is 1 meter long. So in order for the edge of the spout to be at the origin, this would need to be 1 unit away from the y-axis here. And then we know that this circle has a radius of 3 meters. So basically, if we go from this edge to the center here, that should be at x equals 4. And if we go 3 more meters, that would be at x equals 7. So basically, we have a circle which has a radius of 3 and is centered at the point 4, 0. So what we want to do is think about what would be an equation for that circle. Well, in general, the equation for a circle is going to be y minus the y-coordinate of the center of the circle, which in this case is 0. So it's just going to be y squared plus x minus the x-coordinate, which is where the center of the circle is, which in this case is 4, all that squared, and that's going to equal the radius of our circle squared, which is 3. So 3 squared. So what we can do is take this equation and solve it for y. So basically, if we just subtract x minus 4 squared from both sides of the equation, that will accomplish solving for y. So that's going to give us y equals, or actually, I'm sorry, y squared equals 9 minus x minus 4 squared. And then if we take the square root of both sides, that's going to give us y equals plus or minus square root of 9 minus x minus 4 squared. So if we want a formula for the radius of our disk, which now you can imagine our disk kind of going through like this, the radius of each of these disks is just going to be the distance from the center, the x-axis, up to this function here, right? Which this function up here is just the positive square root piece that we have here. So basically, our radius is just going to be this square root of 9 minus x minus 4 all squared. Except it's going to be xi star instead of x. But it's the same idea. So the volume of our ith disk is just going to be pi times our radius squared, which is this positive square root piece here, right? The reason we want to take the positive square root is when you have a circle like this, the positive square root represents the top half of the circle, and the negative square root represents the bottom half. So the plus or minus square root gives you the whole circle, but we really only need half of our circle to measure the radius of it. So we can just take the positive square root. So we're going to get the square root of 9 minus x minus 4 squared, all squared, because we have our radius squared. And then we're going to multiply that by the height. Well, the height of each of these disks, we call that delta x. And basically all that means is the distance that you go from one disk or one layer of your water to the next. Or I guess I should say it would be delta xi star. And this should be xi star. Or actually, I'm sorry, I'm getting my variables mixed up here. This is just delta x out here. So the xi star represents the just this distance here, but we can just call that delta x. So this equation here represents the volume of the ith layer of our water. So we can actually simplify this, because notice we have this square root here all squared, so those are just going to cancel, and we're just going to get the volume of the ith layer is just going to be pi times this stuff in the parentheses here, or inside the square root here. And then our delta x is going to remain out here. So that gives us the volume of the ith layer. So now what we need to do, now that we know the volume of each little disk, of course dependent on whichever xi star we're looking at, the depth of the tank that we're looking at, once we have the volume, what we need to do is figure out the mass of that disk. So what you want to keep in mind is that mass is just density times volume. So if we already know that the volume is given by this equation here, to figure out the mass of the ith layer, which we will call m sub I, the mass of the ith layer is just going to be the density of the liquid in it times the volume of that disk. Well, the density of water, so we're assuming that this tank is filled with water here. The density of water is just 1,000 kilograms per cubic meter. So to find the mass, we just have to do this volume times 1,000, basically. So that'll just be 1,000 pi times 9 minus xi star minus 4 squared times delta x. So that gives us the mass of the ith layer disk of our water. So once you know the mass, now we can use this to figure out the force that it would require in order to lift this layer up out of the tank. So the force is basically accounting for the fact that gravity is pulling that layer of water down towards the ground. We have to figure out the amount of force that is pushing it down, basically. So force is just mass times gravity. So we already have the mass of our ith layer, so we already know that this represents that mass. We just have to multiply that by gravity to get the force that it's under. Well, gravity is just a constant. Gravity is just going to be 9.8 like meters per second squared. We don't really need to worry too much about the units. Really just doing this mass times 9.8 would give us the force that it takes to lift that layer up. Or, I'm sorry, the force that it's under because of gravity. So just multiplying this by 9.8 would give us the force. So 1,000 times 9.8 is just going to be 9,800. So we're just going to get the force acting on the ith layer is 9,800 pi times 9 minus xi star minus 4 squared times delta x. So now is finally the point where we get to actually use our work formula. So remember, work is just force times distance. So the work required to lift the ith layer out is just going to be the force acting on that disk, which we have a formula for right here, times the distance that we have to lift it. Well, remember, we came up with this variable here, xi star, to represent exactly that, the distance that that layer has to be lifted to get out of the spout. So to figure out the work, we just have to do this equation we have for force times this variable that we came up with to represent the distance we have to lift that disk. So it's just going to be xi star times this whole equation that we have here. So that work is just going to be 9,800 times pi times xi star times 9 minus xi star minus 4 squared times delta x. And this would be the work that it would require to lift the ith layer of our water out. So this, of course, doesn't tell you the work that it requires to lift, all the water out. It just tells you the work required to lift the ith layer out. So what we have to do now is use this to set up an integral, which would give us the total amount of work to lift up all the I layers, or the, every single ith layer, basically, which is all the water. So to do that, basically all we have to do is set up an integral, and we're going to integrate this work that it takes to lift the ith layer But the difference here is now we can actually just change to x, and then when we put it into an integral, this delta x is going to convert to dx. So really that's just telling you basically what the integral is doing is it's summing up all of the amounts of work that it takes to lift each individual layer. It's adding all those up together to give us one total amount of work that it takes to do this. So when you kind of put it into being in terms of an integral, this delta x changes to a dx, and then we can, basically for convenience, essentially just change these xi stars to just x's. So now what we have to figure out is the bounds of our integral. Right, so the bounds is going to represent the range of these x values, basically, that we want to integrate over. Well, where the x came from, again, was the distance that we have to pump our water. So what we have to figure out is, what is the range that we have to pump each layer of water? What are the total range of distances? Well, we can see this very, very, very top layer up here, at the very top of our tank, only has to be pumped. It's already at the bottom of the spout. It just has to be pumped up 1 meter to get to the top of the spout. So the shortest distance we're going to have to pump is 1 meter. So that tells us that the lower bound of our integral is going to be 1. And then this very, very bottom bit of water down here at the bottom of our tank is going to have to be pumped all the way up through the tank and then all the way up through the spout. So if the radius of our sphere is 3 meters, it's going to have to go 3 meters to get up to the center of our sphere, another 3 meters to get up to the top of the sphere, and then another 1 meter to get to the top of the spout. So that's going to be 3 plus 3 plus 1 is 7 total meters. So basically that tells us that the upper bound is going to be 7. So now we can integrate this, and that would give us the total work that it would take. So to do that, what we can do first of all is pull out our constants. So we can pull out the 9800 pi. And then what I would recommend doing is expanding all of this out. So remember, x minus 4 all squared is the same as saying x minus 4 times x minus 4. So if you do that, x minus 4 times x minus 4, FOIL that out, that's going to give you x squared minus 4x plus 16. So x squared minus 8x plus 16, and all this is going to be subtracted from 9 and then multiplied by x. So if we distribute our negative into here, we're going to get negative x squared plus 8x minus 16, and then we do also have this plus 9 here, so that's going to give us minus 7. And then that is all being multiplied by x still. So distributing that x in there is going to give us negative x cubed plus 8x squared minus 7x. So basically the thing that we're integrating is just this right here. So we're going to get 9800 pi times the integral from 1 to 7 of negative x cubed plus 8x minus 7 with respect to x. I'm sorry, I actually made an error here in my distributing. So when we distribute this x here, we should get negative x cubed minus 8x squared minus 7x. So we should have an x squared here. Now when we integrate this, we should end up with the correct answer. And that would be 1,411,200 pi. And the units on that is going to be joules. So that should be it. So like I said, this is one of the formulas on my Calc 2 study guide. There's a link down below if you want to check that out. If you found this video helpful, be sure to subscribe to my channel. I've got plenty more videos like this coming out. Thanks, and see you next time.